Sonika Kurode, and this is my bar magnets lab. So the purpose of this lab was to compare real-life measurements of magnetic fields to those made by a computer model, and so we could see the relationship between magnetic fields and distance to the magnet. So the model was a bar magnet that was close to a phone magnetometer app, and we did it on both the parallel and perpendicular fields. The physics principles involved in this lab is mainly the Biot-Savart laws, which are shown below. So the ones I included is the dB, which is the magnetic field for a dl length of a magnet, the B of a loop, and the regular B equation for a dipole, and then I also included the dipole moment equation. So the main result that I calculated was that the experimental net magnetic field was 7.35 times 10 to the negative 5 t, and the theoretical net magnetic field was 1.34 times 10 to the negative 4 t. So you can see that they were very different, and I'll get into that later. So the system was the magnetometer and the surroundings were the bar magnet. The initial conditions was that we set the x component of the magnetometer to 0, and we treated the bar magnet as a magnetic dipole. So in the experiment, the first thing we had to do was orient the iPhone to the 0x coordinate position, and this would compensate for magnetic north, so that we could just be looking at the magnetic field due to the magnet. Next, we found the magnetometer chip, which in our phone was located in the top right-hand corner of the phone. And after this, we measured the on-axis magnetic field for various x components listed in our graph. And then after we got that data, we measured the off-axis magnetic field. And to get this, we found where the net field was 100t and recorded the y component. Then we recorded the distance to the magnet and corrected the y value using that distance perpendicularly from the magnet. And we repeated that twice and wrote our data down in our spreadsheet. So here is the spreadsheet. You can see all of the data from the distances and the different distances over here with the different t's that we had to look for, which are these t's that we calculated. And then over here is the data we found for the off-axis field, and over here is the graph that was created. So based on this graph, we found that n was negative 1.4289, and ln of k was negative 12.469. And by solving for k, I was able to find the mu for the magnet, the dipole moment, and that was 19.21. So here's my code details. You can see over here I put 19.22 for my mu magnet. Over here is just the function for creating the magnetic field. These are just some distances to create the arrows and locations on the image from the code. Over here are all of the observation locations that we're going to be looking at. And over here are the 4 arrows representing the magnetic field. So you can see we multiplied the B scale times the different B perps to get 4 different arrows. And at the end, we are calculating the observation location 45 degrees from the axis, and that is what we print out at the end. Oh, sorry. And over here, we're taking magnet.mu and r of 45 degrees in the dipole equation to get the magnetic field at 45 degrees. So over here is the output of the code. You can see the little magenta arrow. It's really tiny, and it's b at 45 degrees at distance c, and this is the distance d that was found from the code. So the difference between the experimental data and the computer data is very large. You can see over here the net magnetic fields are like very different, and this is most likely due to various errors that may have been made when collecting data. And the way that I got my theoretical net magnetic field was by finding the magnitude of the B at 45 degrees, which is over here. So the sources of error in this lab came to a lot of different things, which is probably why the difference between the two net magnetic fields are so large. So the magnetometer could have been affected by various magnetic objects in the room. There could be inconsistent phone placement, which would cause variations in distance, and that would create an issue in our calculations. The magnetometer could have had an inaccurate reading because it is a phone app, and we could have also taken inaccurate measurements since we were the ones looking at the distance. And because we took our data over 2 different days, this could create inconsistencies within the data for those 2 days. So finally, what if you hadn't oriented your experiment to compensate for magnetic north? The measured fields for x and y would be different if we didn't compensate because it would take into account the magnetic north. And then this z component wouldn't change because we kept our phone on a flat surface, so the z wouldn't change even if we didn't compensate for magnetic north. What if you were to stick two identical magnets and run the experiment again? The magnetic field would just double, but the direction would stay the same, since the two magnets would just act as one magnet, but with double the force. Thank you so much for listening to my lab. I hope you enjoyed, and have a nice day.